Okay, so let's talk about the concept of linear independence, which is related to the concept of a linear combination. So let's consider a set of three vectors. It doesn't have to be three, but three is kind of a convenient number for me. We'll get more into this later. For right now, I just need a kind of a basic idea. So we're going to say that the definition of linearly independent, so we're going to say our vectors, u, v, and w, are linearly independent. Sometimes this is just set as independent. I'm not a huge fan of that, but it works. All right, so u, v, and w are linearly independent if the only combination AU, oops, that's not a good U, AU plus BV plus CW equal to the zero vector is A equals 0, B equals 0, and C equals 0. In other words, the only way you can combine these things to get the zero vector is when all the coefficients are 0. Right, so the only linear combination of these to equal the zero vector is when A, B, and C are 0. Now, this doesn't seem like it's probably super related to linear combinations. I mean, it kind of, yeah, maybe. The kind of easier way to realize this is really this means that one of these vectors is in the plane made by the other two. So if we rearrange this a little bit, we'd see something like A over CU plus B over CV is minus W. And we could bring that minus sign to the other side, and we could see that W is in the plane formed by U and V. Now, I was only allowed to do this because C wasn't 0, right? In the case that one of these is allowed to be 0, but the other two aren't, you maybe have a little more work to do. But rest assured that some one of them is in a plane made by the other two. Or at least it's in a line made by the other two. Or they're all friggin' 0, in which case they're definitely not going to be a linearly independent set. Okay, so this is linear independence. Linear dependence is when there exists a set of A, B, and C not 0 with this property that you can add them up. So they're independent if they're outside, if all three vectors form a three-dimensional space, right? One of them doesn't lie in a plane formed by the other two. They're dependent if one of them does lie in a plane formed by the other two. Okay, that should be good enough. Now, we'll come back to this concept again later in the course, so don't be surprised when this is eclipsed by a more complete understanding.